When it comes to storage, it seems like you have the option big, cheap, and fast. Pick any two. I can get conventional drives like this that are big and cheap, but they're not fast. I can get solid-state drives that are cheap comparatively and fast, but they're not very big. I could, of course, get a solid-state drive or NVMe device that is both big and fast, but it won't be cheap. So I'm going to show you an alternative today by using logical volumes and LVM caching to take both the conventional drives and the solid-state drives, put them together, and make a software hybrid device that is both big and comparatively cheap and still gets good performance. Maybe not as fast as a large solid-state drive, but certainly as good as we can do in our budget. So on my system, I've already configured logical volumes. I've already got a volume group. And this volume group is backed by two RAID arrays. And I've showed how to set these up in other videos. One, MD0, is made up of a pair of small solid-state drives. MD1 is made up of a pair of large conventional drives. And what we'll do today is we'll take these two RAID devices and combine them together into a hybrid logical volume. First of all, we need to create three separate logical volumes. First, we'll create a large volume on the slow device using LV create VG1 dash size, we'll say 1 terabyte, and we'll call this hybrid. And we'll tell it to store it on dev MD1, which is our large and slow device. Wipe any signatures, yes. And now we will create as well a smaller logical volume on the fast device. We'll say 50 gigs. And we'll call this hybrid cache. This is where we'll actually store the block cache. Alright, and now we'll create one more tiny device for the metadata. Call this hybrid cache meta. And it'll give that a size of 1 gigabyte. And we'll also store this on dev MD0. Apparently we've nearly filled up our device. Well, for the sake of example, we'll give this 700 megabytes. And there we go. Now we need to use LV convert to create a cache pool out of those last two devices that we just created. Pool metadata VG1 slash hybrid cache meta VG1 slash hybrid cache. Type cache pool and then pool metadata. There we go. LV convert dash type cache pool dash pool metadata is going to be the VG1 hybrid cache meta, and then the device is VG1 hybrid cache. Alright, we will destroy the data on that. And now we have the cache pool device that's been created. Now last but not least, we actually need to create the hybrid device, LV convert type cache, and we'll go ahead and tell it to give us a boost of performance for writing as well as reading by putting it into write back mode. Cache pool is VG1 hybrid cache, and then VG1 hybrid. Alright, we will wipe the metadata. Now you can do this on an existing and running logical volume. It doesn't actually wipe the data on VG1/hybrid. So if we already had a volume, say our root device, and we wanted to add a caching device to that, we could. It destroys the data on the hybrid cache and of course the hybrid cache meta devices. But this, the data stays intact. So that's a good thing to keep in mind if you want to add some performance to an already running system. Now that we have that device, we could go ahead and create a filing system on it. Dev mapper VG1-hybrid. And even though it's a fairly large device, it should complete fairly quickly. And we can go ahead and make a mount point for it. Dev mapper hybrid MNT hybrid. And there it is. Okay, so now we have the filing system there and mounted. But suppose we wanted to do a little bit of maintenance on it. First of all, let's go ahead and see what the layout looks like. LVS, again, that just shows us the type of devices. Here we have a hybrid cache, a hybrid C origin. LVS-A gives us a little bit more information there. It shows us not only the devices that we've created, but also these hidden devices that we've created and some others that it created as well. So you see the 1 terabyte hybrid drive, but then you see that hybrid cache of 50 gigs and the metadata of 700 megs there as well. We can do LVS-A-O plus devices, and unfortunately that wraps around the screen a little bit, but you can see that hybrid is on dev, the cache is on dev MD0, but the data is on dev MD1 there. At this point, we'll go ahead and use a sysbench tool to create some files and go ahead and start warming up the cache here before we show you some of the maintenance commands. So sysbench test equals file IO, then we'll file test mode equals, we'll go ahead and create the file sequential write and then run, and that'll go ahead and create some files on that hybrid drive, and then we'll go ahead and run a couple benchmarks. That'll start warming up the cache for us. And we'll do a random write test. Do that a couple of times, and that'll start warming up the cache for us. And then I'll show you some of the different commands. I'll go ahead and keep running this. You can see obviously this is running much faster than it would on a conventional drive. We're doing 10,000 write operations, and that's completing in just a few seconds, over 1,200 requests per second executed. We can do an interesting command here, LVS-A-O, and you can add different columns in here, devices. One of the ones that I like to add in is cache dirty blocks. And you can see that there. Rather than adding that in, let's go ahead and just do it this way. LV name and cache dirty blocks. Again, that shows us 30,000 dirty blocks. So obviously the write back cache is working well. if you put a watch command on that, you can see that'll slowly start moving down as it starts to flush data back to the conventional drives there. Now, there may be some circumstances where you want to actually remove the cache from a cache device. That might happen, for example, if you want to extend that cache device. Currently, Linux doesn't support extending a cached device without first separating the cache and then re-adding it after the cache device is extended. The first thing you'll want to do if you're using write-back mode, which is how I showed you how to set it up, is you'll want to switch the cache policy into the cleaner policy, which will force all of those dirty blocks to be flushed back to the disk. That can take some time, and you'll need to be patient. You won't want to do any more operations until the cache dirty blocks number goes back down to 0. But on a system that's busy, it can take some time. You may need to possibly stop or pause some processes that are writing heavily to the disk in order to allow that flush to complete. But we'll go ahead and switch that policy now into cleaner policy. I'll go ahead and show you cache, let's see here, cache mode, cache policy. There you see the cache mode is write back, cache policy is SMQ, which is the default. We can do LVChange cache policy cleaner, and then we'll go ahead and give that vg1/hybrid. And you need to do this on the underlying tdata device. Let's see here. You just do it on vg1 hybrid. So we can switch that cache policy into the cleaner policy. Now, if for some reason you're working on a thin pool, and this is where I got the tdata, you will need to operate not on the main device, but on the _tdata to switch that underlying data logical volume into cleaner mode. So in this case, we're not working on a thin pool, we're working on a regular logical volume, so you need to use the LVM device. So we'll go ahead and look at that. Notice here, we've switched that cache policy back to cleaner, and it's gone ahead and flushed all the rest of our dirty blocks back to the disk. So that is a good sign. So once that is changed, we could, for example, if we just wanted to change the cache mode, lvchange -cache mode write through vg1 hybrid, and now that's changed. And I can look at that. Write through mode is enabled now. So if I wanted to, I could actually split that cache device back off of the logical volume. I would do this if I needed to extend it, for example. So we could do lv convert --split cache vg1/hybrid. That will split the caching device off. And now if I do the LVS, you can see here we have hybrid, and then we have hybrid cache, which is separated off from that hybrid device. So now I could do lv extend vg1/hybrid --size plus 100 gigs, and now it's extended. And then I could just simply run the command again to convert that back to a caching device. lv convert type cache mode, and then we can do write back mode again, cache full vg1/hybrid cache and vg1/hybrid. And again, we're going to wipe the metadata, and it is now cached. So if we go back to our watch command, there we have, it's in write back mode. Notice the cache policy is still cleaner policy though, so we'll need to go ahead and LV change -cache policy SMQ VG1/hybrid. And that's going to switch that cache policy back, and now you can see that we're building up a few dirty blocks back in the cache, which means that we're boosting the performance, both read and write performance, using the solid-state drives. Just to finish up, let's do a little bit of benchmark comparison to see how much performance boost we're getting out of the hybrid drives. Again, we've got this mounted here. We've got a set of test files. We can do a random write test by using sys bench test equals file IO, file test mode equals random write, and then go ahead and run that test. This is what we did earlier. So there it is with a cold cache. I just did the random write test, and it came back about 99 requests per second. Pretty slow, a lot slower than the one we did a little bit earlier, which is a little bit odd, possibly because the block size here is 16K. I'm not for sure why that is. Let's go ahead and just look and make sure that yes, everything's in write back mode. Let's run some read tests to warm up our cache, and then we'll run the write test again. Sequential read, 10 gigabytes per second. I don't think that's quite right. Okay, the trick to fix this is to tell Linux to go ahead and drop the in-memory caches. So we'll just echo 3 to proc sys vm drop caches, and I like to sleep a few seconds just to give the system a little time to recover from the dropped caches in case it needs to thrash the disk for a little bit, and then go ahead and run that sysbench again. That'll actually force the block device to read those files back. This again is a sequential read test, so it's reading it back from the disk. Of course, since we have a cold cache, it's reading everything from the conventional drives underneath, but it should be also filling the cache as we go. Okay, so there it says it's about 100 megabytes per second. We'll go ahead and run that again. It does actually have some logic built into this so that it doesn't store a huge amount of stuff on the solid-state drive when we're only accessing it through sequential reads and writes. But since this is about the only thing on that drive at this point, if we run this enough, it should start caching things in to the solid-state drive, and we should start seeing a real major boost in performance here after a minute. Yeah, notice we're doubling our speed now on the read test. We'll go ahead and run it one more time and see if that boosts the speed up a little bit more. Yeah, 300 megabytes per second. Run one more time and see what that does speed-wise. Again, this is a sequential read. Yeah, and we're getting at 500 megabytes a second now. Let's do a random read as well. That should give us pretty good performance. Yeah, dropped it down a little bit, but 65 megabytes per second. A whole lot faster than what we're going to get off of a conventional drive, reading random 16K blocks. So run that again. And again, 68 megabytes per second. Let's do that random write test again and see what kind of performance we get. Alright, we're pushing 12 megabytes per second, 778 requests per second, which is almost a 10 times, 6 or 8 times boost over what we had before. Let's do that again. Alright, we're 10 or 11 megabytes per second now. About like what we had before. Again, this is 10,000 write requests, 16K block size. Alright, just for the fun of it, let's go ahead and do that command to split the cache away. Let's see if it's in my command history. 539. And we're going to split that cache off the block device. Of course, it's going to have to flush all of the blocks out. Give that a minute for it to flush. Alright, now it's flushed out. Now let's just do that random write test again one more time, just to get a baseline performance without any caching device. So there's our baseline performance, again, down to 1.5 megabytes per second, or about 100 requests per second. So clearly the caching device gives us a huge boost in performance, and you get the best of all worlds. A comparatively cheap, fast, and large cached device for your big files.